So let's imagine a scenario where there's two people here. There's me, and then there's you. And we are both standing here next to each other, and I happen to flip a coin, and I ask you to call it. The coin can either be heads or tails. So the question is, do you know what the chance is? The chance of getting heads. If your guess was 50%, then you would be correct. So in this case, the chance of getting heads, the probability that you would get heads, or P, I guess you could say, of getting a certain outcome would equal 50%. And concurrently, the chance of not getting the probability, or I should say 1 minus P, would also equal 50%. So the chance of getting a heads and the chance of not getting a heads, or in this case, you could say tails, since there are only two possible outcomes, are both 50%. Now let's take a step back and go back to our first situation over here. There was an assumption that was made when I tossed the coin, and I asked you what's the chance of getting heads, and you said 50%. The assumption you made was that the coin was fair. However, there is no evidence that it's a fair coin. For all you know, the coin could be rigged. It could be a double-sided coin. At that point, the chance of getting heads would be 100%, correct? However, it's not unreasonable to believe that I'm tossing a fair coin when I present you with this question. So the idea that the coin is fair, this is considered the ground truth, or the null hypothesis. That is, when presented with a problem for a coin flip, you think that the coin is fair because that's always how it's been, right? You're dealing with fair coins when you're presented with a problem on coin flips. Same with dice rolls. If I present you with a dice and I tell you, hey, what's the chance of getting, 1 on a dice? What percentage is it? You're gonna assume it's a fair dice, right? Fair dice. This is also a null hypothesis. So the general idea here is there are certain givens that we assume to be true when we're dealing with statistical problems. So taking this back to our coin example, let's say I flip the coin and you guess tails and it flips heads, right? So you, me, you guess tails and it flips heads, and you guess tails again and it flips heads, and then you keep guessing heads, tails, and I keep getting heads, and we keep going on until it keeps getting heads for however many times we do it. And then you say, hey, wait a second, I think this coin is rigged. And I tell you, well, you're gonna have to prove it. How do you prove that the coin is rigged? Your hypothesis in this case, coin is rigged. The null hypothesis is that the coin is fair. So I want to talk a little bit more about this hypothesis in terms of hypothesis testing. So we determined that the null hypothesis, that is what everybody assumes to be true, that the coin is fair, that's the null hypothesis. And your hypothesis is that the coin is rigged. However, I think, Blake, hey, you're crazy. You just got unlucky and the coin is fair, right? So what are the possible outcomes here? Well, one outcome was that the coin is fair. And the other one is that the coin is rigged, right? So this means that you and me and the null hypothesis, let's call this the null. So let's change the color over here. And so if the coin is fair, this means that you are wrong, right? And the null hypothesis holds true for both of these situations. So that means that I was right and the null hypothesis was right. And let's go to the other situation over here. Let's say the coin is rigged. This means that you were correct, and I, on the other hand, it turns out that I was wrong. The coin was rigged, and I thought it was fair, and the null hypothesis also turned out to be not true. So in statistics, we call this whole box here hypothesis testing, where you have an idea and you want to test if that idea is true. So in this case, your idea is that the coin is rigged. My idea is that the coin is fair. And the general idea that everyone accepts is that the coin is fair. You're wrong over here because your hypothesis goes against the null hypothesis, and you were wrong. You ended up making an error, and this error is called a type, my spelling, a type 1 error. Okay, so this situation right here is a type 1 error. The proper idea that most people pick is, like, for example, a jury, right? The null hypothesis here is that innocent, and you think they're guilty, but the truth is that they're innocent. You ended up making an error. This is a type 1 error right here. The case here, you ended up being right over here. So let's say you ended up thinking that the person is guilty and you were right. So you didn't make an error in this situation because you properly went against the null hypothesis and you proved that the ground truth showed that actually the coin was rigged, right? So in this case, I'm wrong. And if I'm wrong over here, I assumed that the null hypothesis was true. So me, I thought that the coin was fair, but the coin actually ended up not being fair. So the null was that the person is innocent, and you, or me, I should say, me thought that they were innocent, and the truth ends up being that they're guilty. So they did not go to jail. So this is what we call a type 2 error. This particular situation right here, where you think that you believe in the truth null, but null is false. So this leads us to our next topic, which is likelihood. Now, likelihood is simply a measure of how well a distribution fits to data. Most of you guys should be familiar with what a bell curve is, or a normal distribution, right? This is a normal distribution, so pretend that my drawing is straight. So this is a normal distribution, and this right here would be the mean, or mu, of that normal distribution, because over here is where the highest amount of values occur. So in the case of the coin flip, let's say I flipped a coin 10 times. So I did 10 flips on a fair coin, and I wanted to count the number of heads. And then I graphed this out. So let's say I did 10 flips and I repeated this experiment 100 times. Well, each time I get 10 flips, maybe sometimes on some experiments I'll get 1 heads, and on very rare occasions maybe I'll get 10 heads. But overall, assuming that it's a fair coin, we expect most times when we flip 10 coins that we're gonna get about 5 heads, maybe 4 heads or 6 heads, right? It should be somewhere within this range. And that's what a normal distribution would look like. Let's say I have a rigged coin. So a coin that's not fair. In the example that I said, maybe my rigged coin, I think it's rigged because every time I flip 10 coins on average, I'm getting about 8 heads instead of 5. Okay, so if we have a mu of 8 heads rather than 5, what we could do is, in order to measure the likelihood that our coin is fair, what we would do is we would take the value on this normal distribution of coin flips and look at where the value of 8 resides. So let's say 8 is maybe somewhere around here. And this value on the graph, this y-axis value, where this is 0, this value of f of 8 is equal to the likelihood. So how do you know if your likelihood score is good? Well, what you could do is you could take the value of 8 over here. So you could take f of 8 and measure against the maximum, which is the f of mu, or in this case, it would be f of 5, in order to get the ratio, the likelihood ratio for how well it scores. So if your score was at 1, which would be f of 5 over f of 5, that means that your goodness of fit is pretty good. But if it's a pretty small score, in this case, let's say f of 5 is some value like 0.2. I'm just arbitrarily picking a value here. So if f of 5 was equal to 0.2 and f of 8 in this case was equal to something like 0.00004, well, we know that this is going to be a very, very small number. F of 8 over f of 5 is going to be very, very small. So how do we utilize likelihood in this case? Because this likelihood ratio is very, very small, it means that it's very unlikely that our coin is fair. So that's one way that likelihood is utilized. So in the case of probability, for example, for probability, we're given the number of tries and the distribution, or the probability, the baseline ground truth. So in this case, the p, right, which would be 50% for heads. So for likelihood, what you're given is, we're given the number of tries as well. So these two are the same, but we're given the result. For a probability problem, I might say, hey, I flipped the coin 10 times. What's the chance that I can get 5 heads? Let's say for a likelihood problem, I could say, given that I flipped a coin 10 times and I got 8 heads, which is the result, what's the likelihood that my coin is fair, that the probability itself, p, is 50? If the p is unknown, you would need the likelihood in order to figure that out. So what you could do is you could take something like the results, you could take your results for your distribution and maybe you could graph it out. So you could do something like, you have 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads, 9 heads, and 10 for 10 flips. And we know that our mean is at this point over here, 8. what was that? This is 8, 9, 10. Okay, so it's over here, 8. So we know that our value is 8. And what we can see here is if instead of this normal distribution, our graph might look something more like this, right? Where it's something like, I don't know, like it starts at 0, then it kind of goes up over here, and then it goes down like that. So because we assume that the data would be normal, we see here that the value, that the score here, it's a very poor match. So in terms of likelihood scoring, this is where somebody, you might want to do something like a maximum likelihood estimator, where you end up trying to use a function in order to calculate where the highest likelihood is for a certain distribution to fit your data. Okay, so just a quick high-level overview of what was reviewed. Probability is the chance of a result occurring with a given and true null hypothesis. So in the example of flipping a coin, I could say, what is the chance that I get 3 heads in a row given that the coin is fair? So I don't have to mention that the coin is fair, you just assume that the coin is fair. So you would just, measure the chance of getting 3 heads in a row, which would be, 1/2 times to the third. And that would be your probability. And this 1/2 over here, that's your null hypothesis. You assume that that's true, and given that you have a null hypothesis that you assume is true, you're now able to solve for the probability because of that. So likelihood, on the other hand, is a chance of a result occurring with an unknown null hypothesis. So given that you don't know what this value is, this is a question mark over here, 1/3. So what is the chance that this coin is fair if I get 3 heads in a row? So given a question mark over here to the third, what's the chance that this value over here is equal to 0.5, that it's a fair coin? And that's where likelihood you score by comparing the distribution of a fair coin to a distribution of what your result actually is statistically. So that's why it's important to get a lot of samples. As you can see in the example I'm showing you, if you flip it 3 times, getting 3 heads in a row doesn't seem so far-fetched, but if you flip it 3 million times, then getting 3 million heads in a row seems very, very far-fetched. So at that point, you could accurately calculate a score value based off of this that could tell you with a statistical likelihood or certainty that something is or isn't what it should be or what your assumption is. Finally, there's also the whole idea behind the null hypothesis. As I mentioned, this null hypothesis of 1/2 being true, if you assume that the null hypothesis is false, but it's true, that means that you made a type 1 error. So basically, in the coin example, it would be the coin is rigged, but the truth is that it's fair. And finally, you also assume, for the second one, you assume null is true, but it is false. So that's a type 2 error. So once again, going back to the coin example, I'm going to be flipping a coin, and I think that the coin I'm flipping is fair, but actually it's rigged. So those are the 2 different types of errors. So hopefully some of you found this video kind of helpful. If you did, then please hit the like button, and if there's anything that you feel I could have done to make this video a little bit better or help you understand the concept better, then please leave a comment and I'll definitely read through all of them. Until next time, have a good day.